All right, this is section 5.1 and 5.2 out of the green book. This is basically getting you ready for factoring. Rules of exponents. You should have had this in pre-algebra, so it's mostly just a review. Although there are a lot of problems, they should not take you very long. Maybe the first section should take you about 10 minutes. All right, so the first thing we're going to be looking at is our rules of exponents. When we look at this situation, they each have a different name. The x, does anybody know what that's called? Okay, yes.
The base.
That is our base, and the 3 is what we call our, what? Somebody? Yep. That's our exponent. And so if I expand it out, it really means this. X times x times x. Okay? When we have like bases, there are special exponent rules that apply. The first one is how to multiply with a common base. When we are multiplying terms with a common base, the rule is to add the exponents. So for instance, if I were to expand this out, n to the third times n squared, this would mean n times n times n, and n squared would be times n times n. And if we count the quantity of n's, we end up with n to the 5th power. Okay, the quicker way to do this, instead of expanding it out, especially if we have like big numbers here. What if I had n to the 49th times n to the 50th? Who wants to write all those exponents out? All those bases out and count them. I'd probably get it wrong just in counting. So we use our exponent rule, which is the third power plus the second power is equal to n to the 5th power. Is everybody understanding?
Wait.
Do this. So now let's look at number 1. 2 squared times 2 to the 3rd. What are we really doing with those exponents, Luca?
We're adding them.
So it becomes
2 to the 5th power.
2 to the 5th. Now let's talk about when we multiply that all the way out. Notice the directions say simplify. If you see simplify or evaluate, they want you to come up with an overall number to multiply that out. So 2 to the 5th is equal to 2 times 2 is what?
4.
Times 2 is?
8.
Times 2 is?
16.
Times 2 is?
32.
So it is 32. To simplify that is to 32. I believe tonight the directions will say write using a positive exponent or write using exponents. If it says that, then we just give 2 to the 5th. Now, number 2 gets a little bit sneaky, and why is that? Why is that? Hershey?
Because you don't see it, but the 3 by itself has an exponent of 1.
Yes, so let's keep ourselves safe, and when we have that, let's add that 1. Let's add the 1. Otherwise, I'm going to get people giving me 3 squared. So 3 squared times 3 to the 1st is 3 to the 2 plus 1, and that is equal to, what is that equal to? Yes. 3 to the 3rd power. If I multiply that out, 3 times 3 times 3, what do we get?
27.
Good. All right. Moving on. Now we have a negative exponent here. Not a negative exponent. A negative in my, is that the base or is that the exponent? Base. Okay, so what would I do next? Nomi?
You would add the exponents and you would get a negative 2
The quantity of negative 2 to the
6th power.
6th power. Now, something to think about. Okay, yes.
It would be positive because it's even.
Right. So we have negative 2 to the 6th power. She's saying it would be positive because it's even. First of all, the negative is part of the base. So it is part of the 6th power. So we are repeating that negative 6 times Anytime it's an even amount, it will end up being positive. If it's an odd amount of exponent, then it would stay negative. And then 2 to the 6th power, we know 2 to the 5th power is 32. What would 2 to the 6th power be? 64. So it'd be positive 64. Now, if that negative were outside, if the negative were outside and it was looking like this would mean the same thing as this. What is the base of the exponent? Only what it's touching, and it's only touching the parenthesis. So only the 2. Even if it was written like this, negative 2 to the 6th power, in order for that negative to be part of the base, what is the 6 touching? Just the 2. The negative is not. This is the same thing as negative. Do you understand the difference there? That's the same thing as negative 1 times 2 to the 6. Is that making sense? Yes, I understand. No, I don't. No? Okay, where are we getting confused at? Which one?
Well, if you had, if it was outside of the parentheses and it was just negative 2 to the 6th power, would it still end up being positive?
No, because the only part of the base, so if it looks like this, and then we have that,
You don't multiply the negative.
what's the base of the 6 is my question to you always. Is it negative 2 or is it just 2? Because only the 2 is closest to the 6. Now, if it were in the parentheses, okay, right here, when we look at this, let's say that, sorry, oh, that's not what I meant to do. If I have something like this, what is the base of the exponent?
The base of the exponent is negative 2.
Is the parenthesis, and what's in the parenthesis? The negative 2. So the only way the negative would be part of that exponent is if it's in parentheses. Does that make sense? Because this, let me do this. This right here means negative 2 times negative 2 times negative 2 is negative 2. 1, 2, 3, 4 times negative 2. Right? 1, 2, 3, 4, 5, 6. Whereas this really means negative. It's like a negative 1 times 2 times 2. Ugh, my nib is bad. Sorry. 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. Are you seeing that? Hershey? Is this clear? Okay. All right, so let's move on. Let's look at a fraction. Oh, let's look at number 4. Number 4 would be, Teddy?
4 would be 4 to the power of 2 plus 5,
Which would be?
which would be 4 to the power of 7.
And you know what? I wouldn't expect you to multiply that out without a calculator. I don't need you to go that big. Fractions. Same thing. Doesn't matter. The base is 1/2. We're still adding the exponents. The 2nd power plus the 3rd power is the 5th power. That means 1 is to the 5th power and 2 is to the 5th power. 1 times 1 times 1 times 1 times 1 is what? Over 32. Okay. What's different about number 6? What's different about number 6? Let's go on to Jack.
One of the bases are different.
One of the bases are different. So which can we use the rules for?
You can use it for the 2 bases that are 2.
Okay. So 2 squared times 2 to the 3rd is 2 to the what? 5th, which we know to be what?
Which would be
2 to the 5th is
25.
2 to the 5th right here.
Oh, 32.
32. And then I'm multiplying 3 to the 4th. This is something to think about. When you have 3 to the 4th, okay, 3 to the 4th, if I did 3 times 3 times 3 times 3, right? 3 times 3 is 9, right? Times 3 is 27 times 3. I can't do that. Not in my head. So, an easier way to do this is to just do them in pairs. 9 times 9. And that I know mentally. 81. It's part of my multiplication tables. Does that make sense? All right, so we end up with 32 times 81, and that you can multiply out. Okay, questions? Yes?
So remember we were talking about the one, it was like 3 where the negative would be outside, so it would be negative 64?
Uh-huh. What about it? If the negative was outside, it would have been, that's correct. It would be negative 64. Yes.
Do we have to show on the side the 3 plus 5? Like,
I'm okay for you not to. Maybe in the beginning, yes, but no, you can probably, as long as you write the problem and the answer. I want the problem and the answer. In case there's a problem, we don't have to go look through a book to figure out what you're doing wrong. So problem and answer is what is required tonight. With my pre-algebra students, I make them write the 2 plus 3. The first time you encounter this, but hopefully this is your second time. You did this last year. All right, so now we're adding a little bit more. Number 1, what would it be, Amri?
number 1 would be x is equal to 7x.
X to the what?
X to the 7th.
7th power, good. Number 2, please, Giselle.
K to the 11th power.
Good. Now, look at number 3. Number 3. What is a coefficient? What's a coefficient? Hershey?
The number that's being multiplied by the variable.
Okay, but it's not just the number. It usually precedes it. The coefficient usually precedes it. It comes before it. So in the first term, it's 3. What is the coefficient of the second term? 1. So I want you to think about this. When we do this, we do like bases with like bases, coefficients with coefficients. So I'm going to rearrange this. Doesn't this mean 3? Write this example down. Times m squared times 1 times m to the 5th. Does this mean the same thing? Now I'm going to use the commutative property. Do you guys know what the commutative property is? What does that mean? Yes.
It means that in multiplication and addition, you can like switch the terms around.
Yeah, we can move them. We can commute them. So I'm going to commute the like terms, the items that are similar. So 3 times 1 times 1 times m squared times m to the 5th. Now, notice over here, they're just straight numbers to multiply. So we multiply coefficients. 3 times 1 is 3, right? But here I have exponents. And the rule with exponents when I'm multiplying is we do what with the exponents? Yes, we add the exponents of a common base. And so we get 3m to the 7th. Now, I don't think you need to write that down every time. I want you to have it down at least once in your example. Does that make sense? Okay. All right, number 4. Who would like to do number 4? Actually, why don't you do 4 and 5? Pause the recording. You do 4, 5, and 6, and then check your answers. Okay, let's check our work. Number 4. What do we have here for number 4, Jacob?
Number 4, I got 7x to the power of 8.
Good. And number 5, what do you think? Shaylin?
So I got a to the power of 5 and n to the power of 9.
Perfect. Okay, questions there? We just moved them around. We commuted. Preston, the last one.
I got -3, a to the power of 9.
Perfect. Okay, questions? All right. So now, multiplying with coefficient. Coefficient with coefficient. Like base with like base. And we use our exponent rules. So let's look at number 1. What would it be? What do you think it would be? How about Sierra?
I think it would be 24a with an exponent of 12.
Perfect. Questions? Questions? Okay, Luca, number 2.
Negative 18, negative 12a to the power of 8.
Yes, be very careful on this a to the first. Make sure you add it there so you don't get lost. Remember, it's -3 times 4, a to the first plus the 7th power. Questions? Okay, why don't you guys pause the recording and do the next 2 on your own. Let's continue. So number 3, what do we have? Let me see, how about Annabella?
We have -18x to the 3rd, y to the 8th.
-18 x to the 3rd, and y is to the 8th. Good. Callie?
I have 30 to the times a to the 3rd times b to the 6th and times c to the 3rd.
Perfect. Questions? All right, moving on. All right, now it gets a little bit more complicated. When we're adding and subtracting terms, first thing you want to do is simplify each side of the subtraction or addition sign. So over here, what does this simplify to, this side that I just underlined? How about Moreno?
It's 7 a to the 3rd power.
Okay, but I want this whole side.
Okay, 14 a to the 3rd power.
A to the 3rd,
And
B to the, and just B. Okay, now if I simplify the other side, Jack.
If you were to simplify the other side, you would get 5a to the 3rd power b.
Good. Now, this is like saying I have 14 a to the 3rd b's, and I'm going to take 5 a to the 3rd b's away. So how many a to the 3rd b's do we have left? Preston?
0.
No. If I have 14 a to the 3rd b's, and I take 5 a to the
9.
3rd b's, I have 9 a to the 3rd power b's left.
Oh, you don't subtract the 8?
Oh, no.
Okay.
This is like when we combine like terms. If I have 2 x's and 3 x's, how many x's do we have? Now, when we combine like terms, we're putting them all into the same pile. Okay? When we combine like terms, we're putting them in the same pile. It's like a kindergartner taking a buttons and coins and separating them. We're putting the coins in one pile, the buttons in the other. We're putting the x's in one pile, the y's in another. This is all of the a to the 3rd power b's all in one pile. I have 14 of them here, and I have 5 over here. And I have 14 here, and I'm going to take 5 of those away. How many are left? 9 a to the 3rd power b. Does that make sense? Yes.
So even if you were adding, you wouldn't do a to the power, it'd still be just 8.
No, it would be 19 a to the third b. The exponents don't change. We can only add and subtract like terms. Let me move over here and take a sidebar. We can only add and subtract like terms if, so we said it was, so if it was like 14a to the third power b minus 5a squared b, could I subtract those? No, because the base is not exactly the same. Do you understand that? Notice this one right here is to the second power and this is to the third power. It has to be exactly the same to combine like terms. Does that make sense? And this is why. Let's just pretend that's x to the third x squared. If I use algebra tiles, this is the tile we call 1 because the unit of measure here is 1, the unit of measure here is 1, and if I multiply it, the area is 1. Does that make sense? Well, if I'm doing this, oops, let's make it a little shorter. Let's say this is a measurement of x, and I multiply it by a measure of 1, what would be the area of this piece? Yes, Ryan? X, right? Because x times 1 is x. Well, if that long unit is an x, and what happens if I multiply it by another x? What would the area of that shape be? Preston?
2x?
Nope. X times x, x squared. Now, I do the same thing. We know that this is x and this is x. Well, what if I add a third dimension? Right? We've got width, height, and I add like depth. What do you think the measurement of this would be? Yep.
X cubed.
X cubed. So when I'm moving numbers around, 1 plus x squared, plus x cubed. Can you understand why x squared and x cubed would not make x to the fifth? Why they wouldn't go in the same pile the same way buttons and coins don't go in the same pile? Do you guys understand that? Because they're different kinds of objects. When I'm combining like terms, I'm putting my buttons in one pile and my coins in another. X cubes are little blocks, whereas x squares are little squares. They're never going to be the same item. You don't put them in the same pile. So the same reason this, because it's squared and this is cubed, it's not the same kind of base. Does that make sense? Okay, well, there's less on this tonight, and we'll definitely hit more of it. So I'm going to move on because we have so many little mini rules to continue with. Okay, quotient of the powers property. Well, before when we were multiplying with like powers, we added the exponents. Now we are dividing. We're going to be subtracting the exponents. Now, I do mine a little bit different. I really don't do, well, let's just do this. If I were to expand this out, right, and then simplify it, I could divide common factors out. So I could take one factor of x, I could take one factor of x and another factor of x, and what's left? What's left in the numerator? Annabella?
X times x times x, or x cubed.
X cubed in the numerator over 1. When I cross cancel, I'm really left with that 1 in the denominator. When I cross cancel there, right? Any number over itself equals 1. So we really make this x cubed. Now, there's a couple different ways you can do this. We can do our subtraction rule. And one thing to think about is if you're doing the subtraction, we always do top minus the bottom. Numerator minus denominator. I just don't know that I can fit it in there. Okay? If you're doing that. So if I take this x to the 5th minus the denominator power, we end up with x to the what? X to the 3rd. Now, I'm not really a big fan of this method because it doesn't help us to build what we need for algebra. And that's where you're going to have really long fractions made up of multiple different kinds of variables with exponents, these complex fractions. So let me show you what I like to do. X to the 5th over x squared. What's the greatest amount of x's we can divide out of both the numerator and denominator? Shaylin? 2. So when I take 2 out here, what's left in the denominator? In the denominator, when I cross them out, what was left over here in the denominator? Ryan? 1. Do you see that? Right here is one place you can see that at, right? When I take 2 of them out in the numerator, how many are left? X to the 3rd. Say x to the 3rd, not 3, because 3 means a number 3. Okay, so now you see we're left with x cubed over 1, which is the same thing as x cubed. Okay, questions there? Nomi, are you confused?
I don't understand how you got to that.
What part?
How it goes from that, well, the fraction to x the 3rd power over 1. Right away.
Okay, so right away, instead of expanding it out right here like this, doesn't this mean the same thing as this?
Yeah.
And doesn't this mean the same thing as this?
Yeah.
And she said we can take 2 x's. We can divide 2 x's out. 1 pair here and 1 pair here. So when I divide it out, what's left in the denominator?
1.
Right, when I divide x squared by x squared, I'm left with 1. When I divide 2 x's out of x to the 5th, I'm left with how many are left when you take 2 out? 3. So x cubed over 1 is the same thing, isn't that the same thing as x cubed? Does that make sense? Okay. So I think we just had to go a little bit slower. Okay, so let's start applying that. Okay, here we go. Now, you see a fraction. We can expand this out. I can expand it. Okay? Prime factors. What makes up 10? Yeah.
5 and 2.
5 and 2. And how many m's? How many m's? 4 m's. And 15, we have 3 and 5 and 1 m. What happens if that said m to the 49th? Do we want to write that out? No, 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 no. So, what's the greatest amount, Nomi, of m's we can divide out of the numerator and denominator? 1. And the biggest number we can divide between 10 and 15. Okay, so look how I'm going to do it my way. I just have that up there so you can see it. First of all, I write the problem and I separate it. Numbers and variables. M to the 4th over m. Isn't that the same thing? Okay. I asked you numerically, what's the greatest number we could divide out of top and numerator and denominator? 5. So 10 divided by 5 is what, everybody?
2.
And 15 divided by 5 is? 3. Good. Then I asked Nomi, what's the greatest amount of m's I could divide out of the numerator and denominator? We always go with the smallest amount. And she said, what? M to the first. So when I take out m to the first, what's left here? The number 1. And when I divide m to the first out here, what's left?
4.
No. When I divide m to the first out of the numerator,
3, sorry.
m to the third. Don't say 3, say m to the third. Now multiply straight across. 2 times m to the third is 2m to the third. Over 3 times 1 is 3. Okay, questions there?
That's your answer.
That's my answer. Okay, try the next one, please. Go. Let's get started. What can we divide out numerically? What can we divide out numerically? Jacob.
Well, I said divide by 3.
Good, and so
I divide, 1 over 6.
1 over 6. What's the greatest amount of x's we can divide out?
2.
We can take 2 x's out of the numerator. We can divide out 2, and what am I left with?
X and 3.
X to the
3.
third. And I can divide 2 x's out of the denominator, and what am I left with? 1. And so when I multiply straight across, we have
X to the third
over 6. Are you guys clear? Okay. Please do come if you need help, because this will be easy to help with. All right. Forget this part. We're going to skip it. It's just summarizing everything. The next part we're going to are negative exponents. Okay. The thing to remember about a negative exponent is a negative exponent is not a negative number. It really implies what kind of number? Does anybody know? Ivan.
A fraction.
It implies a fraction. So x to the negative 1 really means it's the fractional amount. We take the inverse. Now, just like imagine any number, 5, if I turned it into a fraction, what would it look like? Yes. 5 over 1. So if I asked you for the inverse of 5, what would you give me? 1/5. Now, what was the exponent there? 1. So it's still going to, okay, it would be, okay. So now, when you have something like this, we're going to put it into its fraction form. I'm going to turn, because it implies, see the negative 1, it implies it is a fraction. So I make a fraction bar. I drop it into the denominator. And once I put it in fraction form, I lose the negative. Now, what was it originally over? 1, so that goes up here. Okay. Can I erase? Yes. So that was it. Okay. All we're doing is simplifying. So when I have 3 to the negative 1 power, what does that really mean? Ethan, in the front?
I think
1
1 over 3.
over 3 to the first power, which makes it 1 over 3. Okay, the next one. Ryan?
It's 1 over 5 to the first power, which is 1 over 5.
Good. Okay, now it starts to get a little bit different. Volunteer, please. Ethan, Hershey?
Would it be 1 over 4 to the second power?
Perfect.
Simplified to 1 over 16.
Perfect. Okay, did you see that? Notice it's always over 1. We don't, it's that imaginary 1. We don't say anything, but it's there. So it rises to the numerator when I reciprocate it. And when I drop it into the denominator, it becomes the positive power. What would the next one be, Shaylin?
You do, so it'd be 1 over 6 to the second power,
Which is?
1 and over 36.
Good. Okay. Remember what I said about a negative exponent? What are we going to do? Reciprocate. So what does this become? 5 over 4 to the first power. Once I reciprocate, it becomes the positive. It's not going to change it when it's to the first power. Okay, so what do you think number 6 would be? Step 1 would be what? How do I get rid of the negative exponent? I see Luca.
3 over 2 to the power of 2.
Perfect. To the power of 2. And then we say 3 is squared and 2 is squared. Or we could also say it like this. 3 over 2 times 3 over 2. Which really equals 9 over 4. Questions? Yes, I understand. No, I don't. Yes, I understand. No, I don't. What part, Shaylin?
Just a little bit where, I guess, simplify, like number 6 at the end of number 6.
Okay. Step 1, we reciprocate it because it's a negative exponent. It's still, but we take the positive exponent, and then everything in there is to the second power. 3 squared is?
9.
And 2 squared is? Good. Okay, we're skipping these. Okay, next, power to a power. Power to a power, that's when you have exponent inside, outside, or two things being multiplied. Everything in there is to the nth power. So, 3 is squared and x is squared. So what would that be? Sierra?
9x squared.
Perfect. Number 2. What's it going to be, Teddy?
2 is going to be 2y cubed.
Okay, which simplifies to? Two y cubed. How do I simplify that? Notice up here, everything in there is to the second power. Everything in here is to the third power.
Oh, excuse me. 8y.
Cubed, right. Because 2 is cubed, that makes it 8. What about number 3? Let's go with, how about Juan?
You do negative 5 to the second power
Is
is 25
m to the,
with times m to the second power.
perfect. Okay, and then the last one, 4 to the third. You guys understanding?
No, sorry. Where did you get the 8 from?
Because I have to take 2 to the third power. 2 to the third power is 2 times 2 times 2 is 8. Got it? Okay, when you get these longer ones, just remember, everything in there is to the fourth power. Now, if you already have an exponent, we say inside, outside, what operation do we do with the exponents? Multiply. Okay? When they're outside and inside, we call that a power to a power. So it's negative 2 is to the fourth power. A squared, outside, inside, means we multiply. B to the third power times the fourth power. And C is the first power times the fourth power. And so what does it simplify to? What does this simplify to, Luca?
16 times A8 times
C to the 4th, B to the 12th power, A to the 8th. Right, that's right. Okay, questions? Okay, let me do a couple more really quick. Okay, moving on. And now we are, oh my goodness. Okay, power to a quotient. So again, we basically just kind of did this. Everything in there is to the second power. Teddy, don't forget. 2 is squared, x is squared, and 5 is squared. So 2 squared is what? What does the numerator become? Somebody? Luca?
4 times x to the power.
Perfect. Over 25. And 5 is squared. Up here, everything is to the second power. 5 is squared. A squared times the power of 2. B to the 4th times the power of 2. And 3 is squared. So we get 25, A to the 4th, B to the 8th, over 9. Questions? Okay, hold on one second. Let me just see if there's anything else because I'm taping. I think we're good there.